we measure pressures a lot. That's what we do a lot. So when we use a manometer and we measure static pressure, you notice what's in the word? Airflow is not in the word. It's static pressure. So let me ask you this question. This goes into what we're going to be talking about anyway, which is why I'm fine going off on this rabbit trail. What is better, low static pressure or high static pressure in terms of the system airflow? Which is better? Which tells us that the system has better airflow? Low static pressure or high static pressure? Lower static pressure, right? Everybody knows the answer to that question is lower static pressure. That's what you want, right? What is the static pressure of the system when it is off? Lower. So that means we have great airflow when the system's off, right? Hopefully you're getting where I'm going with this. What happens if you set up your airflow, you have a variable speed air handler, let's say it's a carrier, it doesn't really matter what it is, and let's say it's a carrier, and somebody lands the yellow wire on the Y1 terminal rather than the Y/Y2 terminal. Anybody ever seen that happen before? That never happens. Never. Of course, happens all the time, right? What happens when they do that?
Low airflow.
You have low airflow, right? What's your static pressure? Low. So you go up to it, you're like, oh, look, I checked the blower charts. I measured my static pressure, and this thing is working amazing. It is pouring water out of that drain like nobody's business, right? It is working. I've never seen a unit work as well as this one. Look at that. The water's coming out of the drain, and it is cold as ice. The only problem is that it keeps freezing up all the time, and it's not cooling the house very well. So what's the issue there? Well, the issue is the only way for us to know that that happened was either one, catch it, just notice that that's how it's wired and be like, oops, that wire's in the wrong spot, boop, boop. Now it's, oh, hey, now my static pressure's high. Now I have bad airflow. I had good airflow before, now I have bad airflow because now my static pressure's high. Or we could use a device that actually measures system airflow. And the only device that measures system airflow currently is, and I'm not trying to sell this product, I do not have a sponsorship. I gotta say this because sometimes people believe that I do. Does anybody know what it's called? It's called the TrueFlow grid, right? It does the TrueFlow grid measure airflow? The answer is kinda. It doesn't do it directly. It uses an actual pitot grid, an actual pressure measurement grid, but it goes into the filter slot and it measures an average measurement throughout. And you're gonna get, in general, about within plus or minus 6%, I think is what they say. Which plus or minus 6% on an airflow measurement is like, oh, angel singing, right? Everything else you've ever been doing to measure airflow, if you're plus or minus 20%, you're doing pretty good. So plus or minus 6% is pretty doggone good. You could use that, or you could just be good at catching all the problems that could cause the system not to be producing the airflow that it's supposed to produce. Because static pressure alone is reliant on the airflow output of the blower. And if something is wired wrong, or if the blower motor is programmed wrong, or if somebody put in an aftermarket motor, or put in a different size blower wheel, or the blower wheel's dirty, or who else knows what's going on with it, that's not going to be correct. So the point of what I'm saying is that it's not to make you feel bad or guilty, because I hate it when people do that. It's to make you aware that a lot of times we have false confidence. We have confidence that we ought not have. And especially when we're trying to teach a new person, because we kind of know. We're like, well, yeah, no, I mean, I know, of course I know that I got to first check and make sure it's wired right. Of course I know I got to check and make sure the thermostat's set up properly. Of course I got to know that, you know, the wire's on the DH terminal and they don't have someone didn't pull the pin off and now it's running low speed because of that. Of course I know that if I don't have a G call on this brand, that the thing will go down to 50% super dehumidify mode, right? That happens. That's a thing that a lot of people don't know. But the guy you're training doesn't know all that. And if we just teach him static pressure, 0.5 equal good, 0.9 or 1.7 equal bad, right? We're missing something in the story. All right, so we're going to talk a little bit about installation here, and this is not, because some of you be like, well, I'm not an installer. Now, most of you probably don't do a lot of installs. If you ever are in Central Florida and you happen to find a system, or you're staying in a house, say a vacation house, because we do a lot of vacation homes. There's a good chance if you stay in a vacation home in the Orlando market, you may be conditioned by an air conditioner that we service. But if you find one that I installed, my name is on the sticker, then just ask to move to a different house. They'll say, what's wrong? You'll say, it's just the air conditioner's not right and I just need to move. So I am not a good installer. This is something that I want to just be clear about. And it's not because I don't want to be a good installer, but I think my head's crooked or something, because I just don't make things look good, and it's bad. So I want to be clear about that first. But when we're talking about install best practices, even if you're not an installer, you probably have some say in leading the install team. You probably can give feedback on it, and you probably have to correct a lot lot of problems for things that are going on from the install team. So this is why we're going to talk about it. We're not going to spend a lot of time on any one thing, but we're going to kind of go through it. But the first thing is, let's say that you really are doing a install from scratch. Anybody here do residential new construction? Anybody? Residential new construction? Not a whole lot. Commercial new construction? Anybody? A little bit here or there? I think you guys just don't want to raise your hands about anything. Is anybody here, living, breathing, above 3 feet tall? Anybody? Anybody here? No? Wow, we got 40% on that. Okay. All right, I'm out. The pre-planning, planning, post-install, these are areas that often get missed. And we just go straight to demo and install, right? That just goes straight here. Mrs. Jones needs a new system, let's start tearing her out, right? But a lot of the most important work happens in these other things. And so when we say pre-planning versus planning, what I really mean is the stuff that happens before we show up on the site to do the install versus the planning that happens the day that you're at the install. And this could be residential new construction, a project, a commercial project, setting or doing a roof pick. It applies to all of these things. If you're missing these, that's where you should do some work first. All right, so pre-planning, load calculation, all that kind of stuff. I am agnostic to anything but just getting a result that works for the customer, which means that, do I believe in models like manual J, manual D, manual S, these sorts of things? Yeah, because they've been used for a really long time, and the people who made them are much smarter than me. And now it's all backed by software, and it's pretty good. Is it always good? No. What's that?
Based on what you put in it.
It is. It depends on, it's garbage in, garbage out, that's true. But are there cases where tribal knowledge can be married with your manual J? Yes. And I am fine with that. There's some certain things where it's like, look, it says that on here, this is the calculation they're using, but for our market, that's not what I'm seeing. So long as you're being really thoughtful about your results, because in a lot of cases we can be pretty biased about data because we had that one really nasty job where we put it in and we did it by manual J and then the customer's unhappy and we ended up having to tear it out and we lost a bunch of money. That one job becomes really big in our head and we're like, look, forget it, I'm just doing 500 square foot per ton from now on, just being done with it, right? Don't do that. But if it's well educated, it's not emotional, and you're like saying, look, there's some factors here that aren't being properly accounted for. An example would be, anybody knows like ASHRAE 62.2, ventilation air standards. Those standards were not made with the Southeast in mind. They did not make them with the Southeast in mind. And they know that. Everybody's clear about that at this point. And so just following it blindly, like I must follow the standard, like that's not the right thing to do. Use some tribal knowledge to give a result in your market that's going to work out there. But that doesn't mean take the baby and throw it out with the bathwater and say models are garbage, right? Manual J, manual D, manual S, and the softwares that support those software, those systems are really good. If any of you do duct designs, and you actually do them, like real, do them, not like scratch them out, on a napkin type of do them, I would definitely suggest that you look at Quick Model, spelled with a K, 2 Ks, I think it's KW, because it's a 3D modeling software that's actually built on a video game platform. The guy who did it, Russ King, and his son, again, they're not a sponsor or nothing like that. It's just really cool what they've done. And for those of you who have always struggled with, like, why is this so difficult? Like, all these numbers and stuff, this lets you just like stack blocks, and then it does the manual J, manual S, manual D, all that for you. Go through your supplies. I mean, this is another big one. Before you get, so do pre-meetings, go through supplies. Don't you wish, for anybody who does do bigger projects, don't you wish that the contractor would bring you in earlier in the design process? So that way you could say, no, that closet is lined up right on a truss and I cannot put this piece of equipment there. Or where do you expect me to run the ducts between floors here? There's no channels for me to run the ducts. Don't you wish they would do that? We can do a version of that as well when we have projects that are upcoming. Where we sit down with the team and say, hey, what challenges are we having here? Let's make sure that we're planning. What do we do wrong? What can we do differently? Those can be really quick, but that communication is key. For those of you who have worked in organizations where communication is poor, you know how much that can mean.
Can I ask you about the equipment that you're selling in Florida? Are you doing a lot of single stage, low SEER?
Sure. I mean, when you say low SEER, there's a decent amount of 14 SEER, sure.
But moisture issues?
Am I having moisture issues with them?
Contractors now talking to builders and trying to upsell them at least 2-stage or variable speed equipment because of mold you know,
Yeah.
and the issues. So what do you see in Florida?
Even in Florida, saying Florida is like saying, you know, like, it's like saying California. It's like, well, the climate in California, it's like, the state's this long and it's got like 20 different climate zones. And Florida's actually kind of similar to that. And so, you know, coastal and Miami versus Tallahassee are two totally different creatures. Do we have more moisture issues with single stage? I wouldn't even say that we necessarily do, but that goes down to the types of houses those go into. If those of you who work on higher end structures, you know that often higher end structures are built worse than simple houses. Because simple houses, the problems get caught quicker and even you can catch them, because a lot of these issues are envelope problems. To answer your question, if you put everything in the mix, I get what you're saying. We're not necessarily seeing more issues with single stage than we are with multi-stage. But if you kind of control for the fact that, yeah, do multi-stage pieces of equipment, if they're set up properly, do they perform better? Yeah, again, depending on which one you're selecting, because this is another kind of tricky thing. We actually took some two-stage equipment and checked the sensible heat ratio. This is going, we're not even gonna talk about sensible heat ratio in this presentation, but we looked at the sensible heat ratio of the low stage versus the high stage. And even though the system is running longer, when it goes into low stage, it's actually doing a worse job of dehumidifying. If you've ever seen the sensible heat ratios or measured the sensible heat ratios on ductless systems, this is a dirty little secret, because they'll say, the manufacturers will say, everybody will say, this is getting better, so this isn't always true, but for a long time it's been, they would say, these systems dehumidify amazing. Look at the statistics on them, they dehumidify so well. That's true when they're at full speed. But when they stage down, yeah, they run longer, but the sensible heat ratio starts creeping up. And sensible heat ratio simply means the amount of the energy that's going towards sensible heat, i.e. not moisture, versus the amount that's going towards latent heat. So for our markets, lower SHR equals better, even if it's more than it needs to be. Go ahead.
In our market, we put mini splits in basements, right? Very little load for cooling and need to be dehumidified, but it's raising the coil temperature when it's barely inches long.
Yep.
So what's the solution there? A lot of those cases.
Well, the solution is to not put ductless systems in basements. I mean, that's not the answer. Unless you have a ductless system that, and again, I'm lumping all ductless systems into one basket. That's not true. There's large variations. And all of the major ductless manufacturers know about this problem. And they've been telling us they're going to fix it for a long time. But let's back up, because this is one of my favorite topics in the whole world, so sorry that we got off on this. But why do you think ductless manufacturers do this? Why do they do it? So for those of you who don't know what happens, here's what happens. You start up a ductless system, you wire it up and fire it up, that thing is draining like crazy, the space is coming down, you think everything's great. This thing's dehumidifying great, and the answer is it is. But as the set point, or as the indoor temperature approaches set point, what does that system do? It takes the compressor and it spins it slower. Okay, super simple. It spins it slower. What happens when you spin the compressor slower? It moves less refrigerant, right? When it moves less refrigerant, what happens to the head pressure? Goes down, right? What happens to the suction pressure? Goes up. Compression ratio drops. What does that do to the system efficiency? Makes it go up. Well, those of us who are like, hey, I love these ductless systems. What do people say about ductless systems when they're trying to sell them? I love these ductless systems. They're super efficient, right? 30 SEER, right? Well, how do they get that 30 SEER? They get 30 SEER by spinning the compressor slow, right? Do they drop the blower speed when they're spinning the compressor slower? Sometimes a little bit, but it's not proportional, because the controls are often independent of each other. The two aren't really talking in that same way. And the customer can go ahead and jack that thing up to high speed all the time if they want, right? Oh, I want it to cool better. Put it to high speed all the time. So what happens if that's the case? Compressor spins slower, efficiency goes up, but evaporator coil, when the suction pressure goes up, what does the evaporator coil temperature do? Goes up. You get a warmer evaporator coil. Is that good or bad? It's good for efficiency. It's bad for dehumidification. To the degree that there is a model match with our friends from Mitsubishi, which they literally are my friends. They are a sponsor of my podcast and of my show, and I'm going to throw them under the bus right now. There is a model match in which the sensible heat ratio is 1. Do you know what a 1 sensible heat ratio means? That means no moisture removal. 0. Right?
We call that the Arizona model.
They call that the Arizona model, right? And is that bad? No, it's not bad. Like you said, if it's in Arizona, it's good, right? You want as close to 1 sensible heat ratio in arid climates because you don't want to pull moisture out of the air. You probably won't anyway. But in our market, that's a major problem. So here's what you do. You choose ductless systems based on a tested sensible heat ratio value at an unloaded condition. Fancy words means when the set point temperature and the room temperature get close together, where it's still running, just make sure that it's still got a good sensible heat ratio. And using something like MeasureQuick, that's actually very easy to do, very easy to do. If you can find one, use that. If you can't, then you're stuck with using a whole house dehumidifier, probably, some type of dehumidifier in conjunction with a ductless system. Or you could use something like the SD12, the Santa Fe SD12, which it actually cools a little bit and is a dehumidifier. It does both. But you got to select your equipment appropriate to the situation. The idea that the manufacturer and the manufacturer's rep and the sales guy is going to do that for you, they're just not. And they're not trying to yell, they're not trying to lie to you. They just don't know, a lot of them. They haven't thought through these situations. Some do.
On the dry, that's not normal, like if it's a multi-stage. A lot of times dry notes, they don't tell you, I haven't read up. And I had, the same thing happened, I remodeled my basement, put a two-zone, put one in the bedroom, and it did dehumidify. So I had a portable dehumidifier sitting underneath it.
Right.
Just that, and then when I put it in dry mode, that would start heating like crazy.
Yeah. Yeah, I mean, they have, the whole unit starts to condense, basically. The blower wheel gets down to temperature. I mean, if you think about the position of that blower wheel, have you ever wondered why they get so nasty dirty all the time? Because they do condense, and you know they do, because sometimes those suckers will flick water out at you. And that's because that blower wheel is just sitting there just inches away from the evaporator coil, like inches away from it. It's right there. And radiant heat is a factor of distance, right? So that blower wheel is going to become nearly the temperature of that evaporator coil in a lot of cases, wherein it will condense, especially if the evaporator coil is not pulling the moisture off like it should. You know, like there's just, yeah, it's challenging. You don't look to me for prescriptive solutions, like here's the way to do it, but I am a very big fan of integrating whole house dehumidification into humid climate designs anyway. I think it's the way we should have been doing it. But then people say, but we didn't used to have this problem. Yeah, but here's the thing you don't realize, is that people used to open their windows for 10 months out of the year and just deal with it. We used to just deal with it. People don't deal with nothing anymore. And the houses are super tight, which means that it compounds the issue. Like our run times drop, and not just tightness, but insulation. I said tight, I should have said insulation in this case. Actually being tight helps with humidity levels. But when you insulate the thing with R400, and now you've got no heat load, the things don't run. So dehumidification, real simple, because in this market it's huge. Dehumidification is a function of evaporator temperature and runtime. Full stop. If you want to pull more moisture out with the equipment, at least on the equipment side, then run the system more with a lower evaporator temperature. And the easiest way to do that is to put more load in. So if you have a house that's got a real humidity problem, pull all the insulation out of the attic. It'll take care of the humidity problem. It took you guys a second there, see? You're trying to get it. But it is, like I had a guy one time who was like, we're having nonstop issues in our master bedroom, humidity. I even added another 12 inches of insulation and it didn't solve the problem. It's like, yeah, you just made it worse because you took away runtime. But the other part, because the structure and the equipment are not separate from each other, is also infiltration. Always look at infiltration, especially from attics. Do you guys have a lot of unconditioned attics here? A lot of, okay, unconditioned attics are the devil in terms of humidity. They're terrible. Why? Because the dew point in attics, you should measure it sometime. Take a psychrometer up in the attic and measure the dew point. Absolute moisture in the attic is astronomical. You, in some cases, will have dew points that are up near 100 degrees, which means that, just in case you missed it, if there's anything in that attic that is 100 degrees, it will start to condense, right? So you wonder why ducts start to sweat sometimes. You wonder why you sweat sometimes. You get it. Attics are bad. And then what do? We say, well, we really want good lighting in this house. So what kind of lighting do we put in the ceiling? Can lights, right? Oh, but the good news is that the can lights are at least sealed, right? Of course, that would be ridiculous. We wouldn't put things in our ceilings all over the place that are wide freaking open to the attic, would we? Yeah, of course we do. So those are the things we look at. Infiltration to the attic is the worst. So reduce attic infiltration. The way you do that is take the can lights down, put in LED cans that are sealed, And that will help for sure. And anything else that's unsealed to the attic space.
It's better to put the can light on a tongue and groove with sealant.
There you go, tongue and groove, yep. Yeah, I don't know if you, recent podcast I did with Jenry Garcia, he's in the Miami market and does this type of consulting. And I said, what's the #1 problem in our market with humidity? And he just was like, that, tongue and groove. That's it, tongue and groove, that easy. And guess what I have in my ceiling in my house that I built 5 years ago? Tongue and groove. And guess what happens up in the peak of the ceiling? I get a little friendly black paint that shows up there every once in a while that I have to wipe down with bleach. It's weird. Don't tell my wife. You'll be fine. You'll be fine. It's fine. The kids are fine. I know they're all coughing. It's fine. It's probably just COVID. Again, back to pre-planning. Looking at loads, looking at designs, having an understanding of your market is key. Tribal knowledge of your market is important. But know some models. Again, when I said know some models, that could mean differently. Know how to use the models of manual J, manual S, manual D. For a lot of people will be like, I don't have time for that stuff. I'm so busy. I'm not saying if you're a 1 or 2 man show and you've never done manual J, manual D, manual S in your whole life that I expect you to right now start doing it. You can hire somebody to do that for you. There are people, consultants you can get on the phone with and send them some pictures and they will walk through how to do it, and then you don't have to do it yourself, and I'm fine with that. In fact, if you're an old dog and you know you're not going to learn new tricks, then that's probably what you should do at this point. And I'm not saying that, because a lot of people will be like, well, you're taking the skill out of the trade, people should know this stuff. I'm like, I get it, but also be pragmatic. Do things that people are actually going to do. And if that's where you're at, then do that. But know that you do need to have a process for doing, because again, the last time I did a manual J, I don't know either because it was so long ago. Like I'm not just sitting at home. A lot of people imagine, as they hear me talk about this stuff on the podcast, that I just sit at home and do all of the stuff that I talk about all the time. I have done all of it, but that doesn't mean that that's still part of the practice in my business. Meaning the business does it, somebody does it, not me. All right, let's talk about some design considerations. And this is just coming down to think about the envelope. Think about this, what we just talked about, tongue and groove. Is there some sort of calculation factor in manual J that compensates for the fact that some houses use open cans and some use closed cans? This is what I'm talking about. A model is only as good as the inputs, and even the best inputs are going to be flawed at times. They're not going to make up for just bad design or an envelope that you can't control. And you are not going to control the humidity in a bad envelope. Not like a so-so envelope, we deal with that every day, but like a bad one, like where there's gaping holes into the structure, which happens. Like there are cases where fireplaces, all kinds of weird stuff that you'll get where you'll have just openings into the space. If you work on 80%, is 80% open combustion furnaces pretty common in this market? Just open front combustion. You want to talk about a ridiculous design? Like we've been doing that for generations, but in a humid climate, where are you getting your combustion air from? Somewhere, hopefully, otherwise people are dying left and right or having headaches that they aren't diagnosed. But you're getting it from somewhere, and often it's probably the attic. In our market it is. They put a little grill right up into the attic, right there by the appliance. And all summer long, it's just sharing air between where the furnace is. In a lot of cases, it's inside the conditioned space. Now again, if it's a garage, maybe it's not as bad. It depends on the situation. Like that's not a great design. Like I don't know why we haven't gone to, even if we use 80%, because in a lot of markets, like my market, we don't care about the efficiency. We don't have a long enough winter. But we can still have sealed combustion 80%, where it's bringing in the combustion air from the outside. I don't know why we don't do that, but that's neither here nor there. But you got to think about that stuff. There's no compensating factor in manual J for combustion air going into an attic. You just, hey, if a 12 by 12 is good, a 24 by 18 is even better, right? Just give it more. We want to be safe. You get the point. Bath fans, kitchen exhaust, dryer vents. Have you ever been into an attic? Again, I'm assuming we have. You probably have more basements than attics here. Do you have both? More basements? Very few basements, okay. So it's very much like Florida then. I feel right at home here. Crawl spaces?
Not like a northern basement. Because it could be a basement, but it's a basement that's tied to a crawl space that's tied to the outside.
Yeah. If you're taking dryer vents and you're venting them somewhere other than outside, I don't care where, up at the roof peak, whatever. I didn't used to know any better. I said, hey, the code allowed it, whatever. We do all kinds of weird stuff. Bath fans, same thing. Just vent it wherever you can. And there's so much moisture that's contained in both of those airstreams. We want to get it out of the house and as far away from the house as we possibly can.
Drop out the conditioner.
Right. That's exactly the right place to put it. Take that dryer vent and just point it right in the condenser. That will help it in heating season, heat the house better. You put a warm jacket around the outdoor coil. That way it keeps it warm. This is obvious. Always one guy, always one smart aleck. My goodness. Things like thinking about where the dryer vent is to keep the condenser away from it, shrubs, all that kind of stuff. A lot of times we don't plan for this stuff. How many times if you've done installs and you show up, if you work for a company that has a separate sales team, do you show up and it's like, yeah, that condenser's sitting there because it's this big, and this one I have is the size of a Sherman tank, and you're expecting me to put it there? Like, that doesn't work, you know, and that's part of the pre-planning and planning process. Here's an interesting one. Watch out for radiant barriers in the attic. Why does it say that? Watch out for radiant barriers in the attic. Anybody have radiant barriers here? They put it looks like tin foil up against the roof deck, or they use the plywood that has the silver coating on it. I used to think those things were great. And well, in Florida we have them all the time. We have this place called the Villages. Y'all ever heard about the Villages before? It's Florida. Oh, okay, I gotta be careful about the stories I tell next. He does, all right. Yeah, he doesn't have a colored loofah on his antenna, does he? Okay, good. Yeah, all right, well, that doesn't mean anything there, apparently. So I'm just saying, if you go to the Villages, just watch out for people with loofahs on their antennas. I'm not going to tell you what it means. You can look it up later if you want, hopefully with your phone in private mode. Anyway, so in the Villages, they really love radiant barriers. And so what a radiant barrier does is it prevents radiant heat transfer between the roof decking and the attic space. Okay, what does that mean? Radiant heat transfer. It's the easiest way to explain it, because this is something people don't realize. And at first, I'm going to give you my favorite example of this that we don't think about. We think of radiant heating. When you walk out in the sun beats down on you, it heats you up, right? That's an obvious one. And can the sun heat you up hotter than the outdoor temperature? Yes, it absolutely can. We know that, right? You take something, you set it out in the sun, it can get much hotter than the air temperature. And that's radiant heat. It's electromagnetic energy transfers from the sun. We get that. We get that when we sit in front of a campfire. We can put our hands like this, blocking the light from our face, and our face isn't as hot, right? We understand that. But have you ever thought about if you're in like a northern climate and there's a really cold wall and you're exposed to that cold wall, that you feel chilly, even if it's warm, even if the air is warm inside the space? That's also radiant heat, but you're the radiant heat radiating heat to the cold wall. That's called radiant cooling. Or actually, you're radiant heating the wall. Anytime there's a temperature difference and there's line of sight electromagnetically, which is another way of saying visually, but there's this whole spectrum of light that we don't see with our eyes. Call it light, call it electromagnetic waves, whatever. But if that wall back there in the back of the room is hotter than my body, then I am going to pick up radiant heat from that wall. And if that wall is colder than my body, then I'm going to give up radiant heat to that wall, even if the air in between doesn't change temperature. Does that make sense? Does everybody get that? That's how that works. It's not just a light thing. It's not just like standing in the sun thing. But here's an interesting thing about radiant heat. I could take a hot skillet, for example, and I could take a piece of tin foil and lay it over the hot skillet and put my hand on the piece of tin foil, air gap in between, I just lay it over, put my hand on the piece of tin foil, and my hand would stay cool for a while. Eventually, it might heat up a little bit because there is some radiant heat absorption, but that tin foil is very good at not picking up that radiant heat. Why? Because it reflects it back. That's what it does. It takes that electromagnetic energy, rather than absorbing it, just sends it back where it came from, right? Make sense? Y'all with me here so far? Okay. What happens if I take that tin foil and I push my hand down on it onto the hot skillet? Now it's conduction, and that's a different story. And you will feel it, right? So here's the first thing. You can't squeeze a radiant barrier. If you squeeze a radiant barrier, it no longer is a radiant barrier. It is now a conductive barrier, and it helped absolutely nothing, probably made it worse. So this is pertinent to nothing that I'm talking about really, other than just the topic of introducing this concept to you. You can't squeeze a radiant barrier, right? So what do? They take this attic decking, and let's say that it's just got a facing of silver on the back side of it. The plywood comes with the radiant barrier on it, right? It's relying on the fact that there's an air gap on the other side. So what is it doing? It's preventing the rejection and absorption of heat from the mass, the material, the stuff in the attic and the roof deck. So what does that result in? Well, it results in the roof deck itself getting hotter. The roof deck itself, now it can't reject into the attic, so it's going to be hotter. The roofing material is going to be higher temperature, which means that radiant barriers aren't great for your roof. itself because now your roof stays hotter, right? That does happen. Is that a big deal? Probably not, right? But it's true. But what does it do to the mean or average temperature of the surfaces in your attic? What happens to them? They drop, right? That's good. Cooler attic equals hooray. But here's the trick. What does it do to the temperature of your ductwork that's running through the attic? It also lowers that. Uh-oh. Because what can tend to happen in that unconditioned air mass? Well, it's stagnant. It's still hot as blazes up there. Maybe not as hot because it's not receiving the radiant heat, but it's still hot, really hot. The dew point is still really high. It's still really humid. But what did you do to all the surface temperatures in your attic? What did you just do to all of them? You lowered them. If they were close to dew point before, and now you put a radiant barrier in, guess what happens? You create a rainforest in your attic, which is fun for all the little things that want to live up there. If you've had a case where it's like, I don't know what just happened, but this ductwork started sweating, all the vents started sweating, everything started sweating all of a sudden, watch out for radiant barriers. Watch out for uncontrolled attics altogether. Because one nice thing about ventilation at the very minimum, even though the attic is still hot, the dew point in the attic tends to stay closer to the outdoor dew point, which that sounds bad, but it's really good because attics can get really bad. Ventilating attics for humidity, pretty good so long as you're not causing an air exchange to the space. Case in point, make sure that your attic, if it's unconditioned, is sealed as well as possible to the space, full stop. If you want to go to really solve the problem, then completely seal the attic and put a dehumidifier up there. So CFM is what? What does it stand for? Cubic feet per minute. So that is a cubic foot, a box of air per minute moving. Every CFM into a house has to come back out of the house every time. Now, with a typical air conditioning system, heating system, it's just recycled, right? You put one in, you take one out all the time. But if anything disrupts that balance, anytime a CFM of air goes outside of the house, what happens? Another CFM comes into the house. It just does. You're not going to keep it from happening. It just does. When you take a, I don't know, whole house fan, you take a bath fan, you take a, this customer they got a new range hood that they're really proud of, even though they never cook, they just like to run it, 1200 CFM, woo, sucking. Well, if you're running 1200 CFM on your range hood, you're sucking in 1200 CFM from the outside. And if you have gaps and cracks to your attic, you're probably bringing it in from the attic. If in this case you're venting out of the attic, which attic ventilators, a lot of people, solar attic ventilators, that's going to solve the problem. You want to make it sealed to the house and you want to make it really easy for air to come in from the outside. Otherwise, you're going to depressurize the attic and it's going to suck air in from the house into the attic, and then the house is going to suck air in from underneath the doors and around the windows and everywhere else. And that air outside is humid, right? So it causes a problem. It's all pretty simple. It really isn't that complicated. And you don't need to be that great at math as a technician to catch on to these problems, but it's just not what you think. We always are trying to solve the problem with the same solution. And I learned this the hard way. So anybody here watch golf? Any golfers here? You seem like a group of golfers to me. You just look like golfers, There's this guy named Marco Mira. He's an ex-Masters champion. It was during like the Tiger Woods era. He lived in the same subdivision as Tiger Woods. I used to work on those houses. And we installed all these new systems, and the vents just kept getting stuff growing on them everywhere. And I was panicking. So what was I doing? I was like taking insulation and just like piling it up over the vents. I didn't know what I was doing. I was just trying all kinds of stuff. Well, eventually it gets so bad that he's got all this growth on a vent that's right over top of his master bed. There's just mold everywhere. I just said it, the M word, right? A moisture problem. Right over top of his master bed. And I thought I had fixed the problem. I probably didn't. But what is my job now to do? It's to make it stop looking like that. What are you supposed to do when somebody has like a California King waterbed in the middle of the room and the vents right over the center of it? What are you supposed to do? I ask you because I didn't know. I was 19, 20 years old. So I set up a ladder on the guy's freaking bed, like this.
Oh my God.
With bleach, doing this. And just thinking this whole time, like, because I watch golf, I like golf. Like, this guy's one of my heroes. He's a nice guy. I'm in his house. I'm just imagining this guy walking in, seeing me do this. And that was the impetus for me to figure out how this stuff works so that I never have to do this again. And I'm not joking. That's actually how that happened. More design discussions to have with the customer. This is sort of my ultimate AC installation. And it has some stuff in here that's, maybe a little more controversial. The more controversial parts would be the APCO X here in the supply duct and the UV lights above and below the evaporator coil. I'm not a huge fan of those technologies in general. I've been pretty outspoken about that. But there's a place for them. UV I'm fine with, as long as it's done properly. PCOs, be careful, with them. It's not something that we just throw in every house. That's my opinion. But the other stuff here is worth noting, and this works very well in our environment. And these are things that I wish we would have more conversations with our customers about, because ventilating dehumidification, when done properly with good equipment, is a really nice technology. It really works great. Because we know, especially in the COVID era, that ventilation air, outdoor air, is great for our health. It really is. Dilution air is great. And it's not just great because it smells fresh, it's great because it actually dilutes the viral concentration within a structure, because it's not just a matter of having one little virus just land in your nasal passage, it's a matter of the concentration of it. And does anybody here think that we're never going to deal with a viral pandemic again ever again now? Anybody think that? No, we're going to. Like, this is going to happen. And so having some solutions that we can provide is going to be a really good thing. So ventilation air is part of this. But you can see we're bringing in ventilation air. Here we're using an ECM blower box so that we can independently control the ventilation air. This is a Mac Daddy system here. It's going into a ventilating dehumidifier, and then it's going into the supply air. Why do we put a ventilating dehumidifier, or a dehumidifier at all? Why do we dump it into the supply air and not the return? Anybody know? Why wouldn't you dump the dried air from the outside into the return rather than the supply? The answer is, well, I like that answer. That's actually really, that's a good way of saying that. Yeah, he said it's where the driest air is. Now here's a tricky thing. Has anybody ever measured the relative humidity in the supply duct? I just want to be clear about what we mean when we say dry. It's very high relative humidity. If you've never done it, do it sometime. It's going to measure somewhere between 90 and 98% generally. How on earth could the air in the supply duct be 90 to 98% relative humidity when it just went over the evaporator coil, you saw the water come out and drain out the drain, and in this return it was 50% or 55% or 60%, hopefully less than that.
Because it's relative.
Because it's relative to temperature, right? Exactly. When you cool the air, you shrink the size of the sponge, right? Shrink the size of the sponge, it can hold less water. It's 100% full because you squeeze it down. When it gets back into the space, then it expands back, and now the humidity percentage drops way down. But when it's in the duct, it's high relative humidity, but to his point, it's very dry in terms of absolute moisture, right? And that's why cold air is dry air in terms of absolute terms. You could have cold air that's 95% relative humidity, but it's still going to be low moisture compared to a hot summer day anywhere, because cold air can't hold much moisture. It could be 100% full and still not have that much moisture in it compared to hot air. And that's why attic dew points tend to get so high, because hotter air can be more full of moisture. It doesn't mean it is, but it has much more capacity. It's a much bigger bucket. It can hold much more water. All right, so why do we put dehumidifiers into the supply air? This is just something you do. I'm not giving you the option. I am, by royal decree, stating that you do not put dehumidifier air into a return. And here's why. That air conditioner is a very good dehumidifier. It is very good at it. But what's the problem with it? Why isn't an air conditioner? Because salespeople have said this for a long time. Well, hey, look, if you got a good air conditioner and you size it properly, you never need a dehumidifier. Never. But what's the problem with that statement? What's the liability of an air conditioning system? Well, it's going to break eventually. That's one thing. What's that?
Load conditions, it's not all right.
And partial load conditions. That's exactly it. Because if you design that system, you're designing it so that it can cool the structure during the hottest day. You are designing it that way. So when you're in part load conditions, it's going to struggle. Now, they say, well, yeah, but that's true of old systems. But what if it's an inverter-driven system? Or what if it's a multi-stage system? Well, that solves that problem, doesn't it? Ha-ha, I gotcha. What's the problem with that? The problem is that regardless, it's still cooling the space. So no matter what you do, it's still cooling the space. And unless you need cooling, it ain't going to dehumidify. And at times, during certain seasons, during certain points, you're gonna have some of your worst moisture conditions in the mornings, in the evenings, sometimes when you really don't need it to run at all. So a dehumidifier, if you want it to maximize its, or optimize its capabilities, you don't want to dump a bunch of dry air in the return, because what's that going to do when the system's running? It's going to derate its ability to remove moisture because you just dried out the air going into the evaporator coil. So now the air conditioner is not going to dehumidify as well. The next thing is that now you're going to recool that air if it's running. One of the actually big advantages of a dehumidifier is that it does actually add some heat. That heat increases the load, which makes this equipment run more. So now it's a double whammy. It's increasing load, it's helping the equipment run more, and it's dehumidifying. Now, people will say, yeah, but that increases your power bill. Yep. Any other questions? You know what else increases your power bill? Running your air conditioner at all. So if you want to decrease your power bill, throw your air conditioner in the dumpster and never run it. Well, it can't do that, exactly. And if you're having a moisture problem in your structure, because of your climate, because of the way you're living in your home, then you need to have a dehumidifier. Now, what are the houses that are the greatest risk of issues? Tight houses can be. There's an advantage to tight too, though. The advantage to tight is if you really are tight to the attic, that's good because that reduces infiltration. Here's my list of bad. Number one, bad structure. So bad envelope. Now, when we said tight, by that, if we meant new, then I would agree, because newer homes do tend to have more trouble, and we'll talk about why that is. But bad envelopes that are leaky to the attic or crawl space or outside, those do cause more problems. But if that's the case, fix that problem, or get somebody else to fix that problem before you go trying to solve it. Blower doors, this is where things like blower door testing and envelope testing come in really handy. Not on every house, but in cases where there's potentially an issue. So that's one. Two would be installation issues with the equipment, and that would include things such as leaky ductwork, that would include things such as the equipment not set up properly, that would include such things as the system not charged properly. Anything that makes the equipment not work right is definitely on the list of dehumidification. But here's the third one, and the one I'm getting at. It's customer practices. The houses that have the worst issues with growth in the houses are houses where the people keep the temperature really low. You know why your grandma and grandpa didn't have these issues? Because they weren't entitled monsters, unless they live in the villages. I did not say that. No, the point is that there was an entire generation of people who they saw air conditioning as a luxury. It was a luxury. Heating wasn't a luxury, because you die. I had a lady one time in the middle of the night who called me, 3 a.m., something like that. This is before I had my own business. And I had the on-call phone. You remember when we used to have that? It was actual phone, and they would leave a message, and you'd have to call back the message, and you'd have to write it down. And on the message, she said, "I have a parrot. It's a very expensive parrot, and it cannot handle these temperatures. You need to come immediately." And I thought to myself, lady, do you know where parrots come from? Because it is not Wisconsin. But that is, I mean, there is just a general sense of entitlement that surrounds air conditioning, and that's okay. I'm not doing a social commentary here. Yes, I am a little bit, but it's just a reality, right? People view air conditioning as their life's blood. And if they want to keep it at 67 degrees inside their home, then by golly, that is their right to do. Right? That's how they feel. And I agree, it absolutely is. And it's also their right to lick the mold off their walls and ductwork that grows when they do it. That's just how I feel about it. So, and why does that happen? Why does mold growth result from people setting their temperatures lower in the space? Lower dew point, right? Lower dew point. Lower dew point on the outside of your ducts. Lower dew point on everything, on the walls and the inside. You'll see cases that are so bad where you'll actually begin to get mold on the inside of walls that aren't even related to the air conditioning, just because maybe there's a vent over here that's blowing, something like that, and you'll start to get mold on the wall there. Here's another interesting one. Do you ever have furnaces or air handling units that are installed in closets in unconditioned spaces like garages or anything like that? Do you ever have that? Have you ever pulled out a unit, pulled it out, and behind the unit is this big black spot right behind where the evaporator coil is? If it's a furnace, it'll be the top portion here. If it's a fan coil, it'll be the whole thing. It's because the proximity of that wall to that unit, and the box is colder, even if the unit itself wasn't sweating that bad, what it does is it translates radiant heat from that box to the wall. Radiant cooling, so it's radiant cooling the wall by the unit. and it causes that wall to hit dew point. Similar things like that can happen and are much more prone to happen in houses where they have the set point lower. Because if you have a 20-degree delta T and it's 75 degrees inside, what's the supply air temperature? 55. If they keep it 68 inside the house, what's the supply air temperature? 48. That means ducts, everything is going to be more prone to sweat. In markets where the humidity isn't high, have at it. Set it as low as you want. And I get in this argument all the time because I'll say these things and somebody in Arizona or Utah will pipe up and say, that's ridiculous. We give all of our customers, 4 or 5 ton units in order to cool a 1,000 square foot house, and we do it all the time and it works fine. It's like, yeah, have at it. If you don't have issues with moisture, then do what you want. But in our market, it's definitely something to think about. Moisture issues with vented attics is also really big. So this is another sort of entitlement dichotomy. You'll have people who buy really high-end units. So they buy a Carrier Infinity, or they buy whatever the Lennox Signature Dave's Signature Series, or whatever Ream is called nowadays. Buy this highest-end unit and they put it in, and they buy it because it's what? Energy efficient, right? It dehumidifies really well. And so what do they do in response to that with their set point? They say, well, before I kept it set on 77, and now because I have this efficient system, I'm going to set it to 69. And I think that's okay to do because I'm paying so much less for this. That does happen. There are people whose behaviors change after they purchase a new unit. And what's the salesperson's favorite line to say when they're selling a unit to somebody? We're going to get it so cold in here you can hang meat in here. Why do we say that? Who wants to do that? That's a ridiculous idea. I don't want people hanging meat in their house. That can't be healthy. That's not good for your children. Don't hang meat in your house. New policy. Salesmen are not allowed to sell meat coolers to our customers anymore. And so you do that. And so customers will come away with the idea that somehow they can change their behavior. And a lot of times it is behavioral change that results in issues like this with moisture. I mean, we know that this happened when was anybody around, I'm asking this tongue-in-cheek, was anybody around during the transition from mercury thermostats to digital thermostats? Yeah, I mean, quite a few of us were. And you would put the digital thermostat in, and the customer would be unhappy. And why would they be unhappy? Because I used to set my thermostat to 83 and I was comfortable, and now I have to set it to 73 in order to be comfortable, right? Because the inaccuracy just so happened to be to a degree where they felt really good about their set point, but it didn't represent reality. And this is kind of a similar sort of thing that occurs with high-end equipment, especially when we sell it improperly. And this is where, when you have really, this is something I'm just going to encourage you, if any of you work in really high-end homes, especially if you're installing it right before a new client comes in, or they're making significant changes to their home, maybe they just bought the house and now they're making all these changes, or you know that they have some objectives that aren't realistic for your market, don't just deal with the equipment. Because if you put that equipment in, they're going to blame you for everything else that's wrong with that house. They're going to. We've walked away from so many jobs since learning this that it's not a joke, because we've realized that there's a group of people that think that money buys them irresponsibility and habits, and it does not. Money buys you a really good air conditioner. It does not buy you me solving the issue because you have an unvented attic and now you want to set it to 68 degrees and now all your ducts sweat. I can't fix that. And what I can say is, okay, get your attic completely sealed and dehumidify it. And then I'll come back and you won't have this problem anymore. Well, I don't want to do that because that costs $70,000. I can't fix the problem, right? But we learned that because early on we would go in and we would just sell it. But they hold us responsible for it. So in the sales process, as you're doing the pre-planning, just plan for that, address it. Generally helpful duct upgrades. It's a very non-committal title there. Generally helpful duct upgrades. One thing that we've learned is that if you can upsize ductwork nearest the equipment, that's where it has the greatest impact in system operation. There was like a group of people for a while who got really bullish on always replacing all the ductwork. And that's fine if you can do it, and that makes sense. I think that's a little unrealistic. I would just say if you can make significant upgrades of any sort that are going to impact the system positively, then do it. And my favorites are the ones listed here. Oversizing the ductwork nearer the equipment. Now, a lot of people will say, but yes, you can oversize ductwork, right? Depends on what you mean. Could you oversize a return and a supply into a particular zone wherein the return and supply are imbalanced, causing a negative or positive pressurization to that room? That could result in a problem, yes. But can you increase the return size, the return trunk line to the unit in such a way that it's going to substantially impact the unit negatively? And the answer is no. In fact, if you look in ACA Manual D, it has this little note that says, while there's some truth to the fact that velocity could cause additional gains in the ductwork, it's so negligible as to be essentially a pointless conversation or something like that. That's when it comes to trunks, make them bigger if you can. And usually we're limited by space, and so that's kind of your limiting factor. That's not to say that we don't pay attention to our registers, diffusers, those designs. Of course, we absolutely have to pay attention to those because now we care about the velocity into the space so that way we can control for throw. But if you show up on a unit and you can resize the return riser or the return going into the unit, well then upsize it. If you can increase the size of a filter back return air grill significantly, well then do it. That's gonna be a great benefit to the customer. It's gonna be much better than selling them some fancy new doohickey that they're gonna put on and just get mad at you about later. Here's looking at you, Nest thermostats. Better filtration. This is another one. You know, all of us, I think at this point, love media air filters. I mean, they're great because it gives you more room to work if you can get them in there. They protect the equipment really well. They generally seal in place a lot better than the factory filters. That's the kind of the thing about 1-inch filters in the factory filter slots is they're terrible. Like, have you seen the gaps around a filter in a carrier unit? I mean, it's ridiculous. So much air can go around that filter. So even if you put a good filter in there, it's just gonna go around it, and that good filter is gonna increase static pressure and all that. So one of the things that we don't think about a lot is, if we can put a filter that's significantly larger in, so let's say that we got a return riser or something coming down near the equipment, and we can put something larger in place, larger filter cabinet. What does that do to the air velocity, the speed of the air moving across the filter? If I put a larger air filter in, slows it down, right? So not only does that filter take longer to get dirty, which is good, but the air's moving slower. So the air moving slower over the filter media does what to its ability to catch stuff? Increases it. You've made the filter last longer. You save the customer on maintenance costs, hopefully. You've decreased your return static pressure because now you have a bigger filter, right? So lower pressure drop across the filter, which does what to your system efficiency? Increases it. What does it do to your system capacity, potentially? Possibly increases it. What does it do to your system longevity? It's good for it, right? The motor, ECM blower motors, X13s, number one reason the things fail is because they're running past their design static pressure, meaning they're having to run faster, meaning they're running hotter than they ever were designed to, meaning they're designed to for short periods of time when the filter gets dirty. They're not designed to run above their stock speed all the time from the moment that they were put in because the ductwork's too small. And then it also increases filtration, meaning it cleans the air better. So we've helped them with indoor air quality, efficiency, system longevity, and system performance, all with one small move of saying, hey, rather than putting one in this big that goes under the unit or fits right here, I'm gonna move it up the riser and make it a little bit bigger. Things like this can make a really big difference. Consider downsizing equipment. Downsizing equipment is amazing. Have you ever gone in where you replace a 5-ton with a 3.5 or with a 4? I mean, that is awesome. You know what just happened to all that undersized ductwork? It just got better sized. Not necessarily right, but it's better. All the way around. The whole shebang just works better. Downsizing equipment is amazing, unless it doesn't cool in the summer, and then it's hell. But that's a whole other thing, and we've all probably done that. But if you do 30 jobs and you get it right, and you get the one that you downsize it, and now on the hottest summer days, yeesh, it's not great. Well, then deal with the envelope. Go in and add some more insulation. Do something with the envelope that gets the load down a little bit. The customer's gonna be happy. Like, I hate it when I hear people do the thing where they're like, I did a load and it came back a 3.5 ton, and I put a 3.5 ton in, and I knew it should have been a 4, and the customer complained, and I tore that 3.5 ton out and I put a 4 in. You're talking about a 1/2 ton. I mean, like, that's not that much. You can deal with a 1/2 ton in an envelope pretty easy. It'd be so much cheaper for you to pay an insulator to go in and insulate a little better in that case. And now you've still got the benefit of a downsized system, bigger ductwork, lower static pressure. It's beautiful. It's amazing. Consider that. Look at that. Be practical about it. Don't just do it because ACA said you're supposed to, because I think a lot of us feel this like peer pressure, like, oh, I know I'm supposed to do manual J's, but man, it's such a pain in the butt, and so I lie about it so that way people don't hassle me, whatever. But if you can do it and you can start downsizing equipment and you can prove that the model shows it and you got the paperwork to prove it, that's a great thing, and it really saves you a lot of heartache. Total effective length. This talks a little bit about turning vanes. I don't know if you do a lot of that here. The main thing is that a lot of people get super excited about turning vanes, but they don't catch on to the fact that the throat here, a smooth transition in the throat actually matters more than a smooth transition in the heel. And the reason why that is is if you imagine you've got a bunch of NASCAR race cars going around a corner, making this turn is going to be much more important for you to have a curve than making the outside turn. Because making the outside turn, you've got room here. You know, you can actually still make it as long as you kind of following. But that's the easiest way to kind of remember that. So a lot of times we do goofy things. I'm not saying turning vanes are goofy, but in terms of the payoff, it's not usually nearly as big as just doing some slightly better designs, oversizing a little bit more. In residential, I'm not talking about big commercial higher velocity systems, but in residential that's the case. And often you run more opportunity of making a mistake where you put them too close together and now it's restrictive and all that. Again, if you've been doing turning vanes and you're really good at it, then keep doing what you're doing. Nothing wrong with turning vanes. I'm not saying there is, but I'm just saying that there's some other things that I would probably suggest before that. And these suggestions are not just coming from me because I'm not in a turning vane market. These are coming from people like Neil Comparetto and Michael Hausch, guys who are really, really good at this stuff in high performance houses. Metal duct, do you guys use metal duct here or do you use ductboard mostly? Mostly metal? Mostly metal, a little bit of both, okay. One thing that we recommend, and again, this comes from, there's actually a podcast that I did, most of this is drawn from this podcast that I did with a bunch of these guys who I consider to be the best at actually doing this in the field. They talk a lot about, you know, as much as possible using shops to do things, so that way you actually get things done properly rather than using crews to field fabricate. But when you have to do it, one of the things that they really suggest is focusing on sealing, because if you're using metal, metal can be very leaky. It's one of the downsides of metal compared to flex. If you take flex and you pull it really tight, at least in that area, you're not going to have leaks and your friction isn't going to be that great. The downside to flex is people just use it to make everything and they don't fully extend it, and so now it becomes a friction rate issue. With metal, it's not so much a friction rate issue. Again, if it's sized properly, it's much more of a leakage challenge. So doing things like actually masticing it, letting it dry before you insulate it, those are things that get missed sometimes. So those are the things to focus on. Flowing nitrogen and pulling proper vacuums are two of the things that you will actually see results in aggregate for. You won't believe that you will, because we all have said some version of, let me quote some things that I've said. That's just overkill. We've done it this way for decades and it hasn't been a problem. Why is it a problem now? Stuff like that, okay? But we were in a pre-POE era. In a pre-POE era, in a mineral oil era, we got away with a lot. Now, pulling a vacuum and flowing nitrogen will save you repairs. It will make TXVs plug less. It will make filter dryers plug less. It will save compressor issues. So just do it. And it isn't hard at all. Here's what I want to say about this, because a lot of times the excuse that technicians and installers use, there's two excuses they use for not flowing nitrogen. Three. One is, I've tried it and it just keeps blowing the last joint out. Okay, you're using too much pressure. You're pressurizing, you're not flowing, and you're using too much. Pull your cores, flow it from one side to the next, right? It barely whisper it. So that's why that's happening. If you still can't do it, then shut it off for the last joint. It'll be okay. You know, like it's not, because again, what we're trying to do is get the oxygen out. The next thing they'll say is, well, I don't want to have to pull the nitrogen out. I don't want to pull the nitrogen off my truck every time you braze. Newsflash, you're supposed to pull the nitrogen off your truck every time you braze anyway. It's called the pressure test, right? So if you're not doing that, we need to talk about that then. I mean, I also remember the days when we used to pressurize systems with R22 for our pressure test, but those are no longer the days we are in. I just got shooshed. The final thing that they'll say is, oh, I don't have the proper regulator for it. My boss man didn't buy me the right regulator, so I can't do it. I can't do it because he won't buy me the right tools and I ain't gonna buy it because it's blah, 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 blah. Look, just take the T-handle on your current regulator that you're using, back it out, take the end that you're purging from, put it up to your ear, and turn it all the way in. No, that'll break your eardrum. No, and just barely turn it in clockwise until you just barely hear it. And that will be fine. yeah, purge with the, no, stop it. You guys are teaching bad things. That's it. If you don't have the right tool, then do that. Oh, and stay bright. I forgot to mention that. I forgot that we are in a market where that is more common, and I am a big fan of Stay Bright 8. So if you're using Stay Bright 8, then you don't have to flow nitrogen because you're below the cupric oxide level. You're not going to get carbon buildup. Well, that's the thing, and again, like in my market, I don't use it. I don't use StayBright 8, and I've explained why, which is one, I would have to retrain my entire workforce, and two, every competitor who went by and saw my joints would think that I was using an improper solder, and I would have to have fights all the time, and I don't want to do either of those, so that's why I still braze. And I know how to braze better than I do working with StayBright 8, so it makes me feel good about myself. Leave me alone. I want to do what I want to do. But on the other hand, you should still, even if you're using StayBright 8, you should still purge with nitrogen. So even after you pressurize, purging is a really good thing, because pressurizing alone isn't the same as purging, because you're still trapping some of that in there, and there actually is the possibility, and it's on the outside, Jim believes this happens more than it really does, but you are actually more likely to condense liquid moisture inside the system if you pressurize before purging. It's the same reason as when you take an air compressor and you compress the air, you actually get water that drops out of that air. Using a purge as part of your pre-process before you pressurize is a good practice anyway, and that's nothing more than just going shh, letting it purge through a little bit and then stop, and it does make vacuums a lot better, especially, and this is true even if you're working on systems that aren't older systems. As you put in a new compressor, you change a component, you do something like that, do a purge before you even do your flowing, and it's a good practice. Or actually, sorry, do your flowing, then purge, then pressurize, then vacuum after the pressurization. Oh, the old triple evac question. Yeah, so that's what we call triple evac. And there's nothing wrong with triple evac, other than that it's a waste of time. For most cases. So if you are in a cold climate and you're trying to pull a vacuum when it's 40 degrees outside, 50 degrees outside, then triple evac's a good idea. It's gonna make it a lot easier for you. But if you pull and hold a deep vacuum, there's the caveat. It's not just a matter of pulling to 300 microns. It's pulling to 300 microns and holding below 500 microns for 10 minutes. You have a good vacuum. It would not pull to that level and hold at that level if you did not have a good vacuum. Yeah, there's the decay test. The decay test is really key. So actually isolating it in the system. We use a one hose evacuation process, which works great. If you do residential installs, the one hose system is just the way to go. And I don't care what hose you use. Jim will tell you got to use the big blue hose. Big blue hose is great, but use an Appion hose. Use whatever big hose you've got. Don't use a 1/4 inch hose. It's just not ideal. Use one big hose, some core tools, isolate it, make sure it doesn't rise too quick, and you're going to have good vacuums, and they're going to go quicker than anything you've ever done. Just no reason not to do it that way. It's not expensive. It's not that challenging. We all know we've been needing to use micron gauges forever, so if you haven't, cracked that one open yet and started using a micron gauge, just start by doing the one hose procedure when you do installs. It'll make me feel so much better, and once you do it, you'll realize that it's easy and it won't be hard anymore. I remember there was a time when pulling vacuums was like really hard because we didn't have the right stuff to do it. And it was like, you've always felt like I did at least, I always felt bad, like I was pulling one over on somebody because I could never hit the numbers that they were telling me to hit. But nowadays, it's not hard.
Thanks for watching our video. If you enjoyed it and got something out of it, if you wouldn't mind hitting the thumbs up button to like the video, subscribe to the channel, and click the notifications bell to be notified when new videos come out. HVAC School is far more than a YouTube channel. You can find out more by going to hvacrschool.com, which is our website and hub for all of our content, including tech tips, videos, podcasts, and so much more. You can also subscribe to the podcast on any podcast app of your choosing. You can also join our Facebook group if you want to weigh in on the conversation yourself. Thanks again for watching.